talked about strong acids and weak acids, and we did a comparison of, we had started with HCl, and we had the same concentration of HCl as acetic acid, and we went through and we found the pH for this. So this is just the review, and so we ended up finding this pH. What we need to do today now is we need to do the same thing, but this time with strong and weak bases instead. So that's our goal. And so first I'm going to do the same idea like we did Thursday. We're going to take a look at kind of comparison of strong versus weak bases. And the comparison is very similar. We're looking at strong bases being ones that completely break apart into ions. So strong bases are bases that completely break apart into ions when dissolved in water. Which is exactly what we said strong acids do. They completely break apart into ions when dissolved in water. And if you recall, there were 6 strong acids you had to memorize. You also have to memorize the strong bases. So, the strong bases are these. They are the hydroxides of the alkali metals. Which column is the alkali metals? The first one. So hydrogen is not an alkali metal because that's a nonmetal. But when I say this, it's like lithium hydroxide, sodium hydroxide, potassium hydroxide, etc. That's what I mean by that. You totally can just look up there. Yeah. I mean, so that's why I'm giving it to you this way. It'll be easier. You don't have to necessarily memorize 6 weird ones. You can look on the periodic table. The hydroxides of the alkali metals and CBS. That's a little mnemonic for you. Because there are also 3 others, and they're in the alkaline earth metals. And so that is calcium, barium, and strontium. Those are in the alkaline earth metals, but those are the only 3. So, you know, things like calcium hydroxide, barium hydroxide, strontium hydroxide, etc. So, hydroxides of the alkali metals and those 3 alkaline earth metals. Those are the only ones that are strong. Weak bases do not completely break apart into ions when dissolved in water. And just like weak acids, they reach equilibrium. And just like the weak acids, this is all other bases. But the trouble is that it's harder to identify bases. It's easier to identify acids. They start with hydrogen, they end with AQ, and it's not one of the 6. Bases are a little harder to recognize, so I'm going to give you a little hint in trying to recognize them. Other bases, they let's just say usually, but they often contain nitrogen. And an example, we'll use this one today, is ammonia. There's in your worksheet, one of the problems uses a weak base, and it's a longer compound, but you'll notice it contains nitrogen. So it's pretty common. And they act as bases in a Bronsted-Lowry way. And what I mean by that is they accept hydrogens. They're proton acceptors. We went through those definitions last week, and so I'll show you that as we go. So what we're going to do is we are going to take 2 solutions of the same concentration, 0.0010 molar sodium hydroxide, that's a good strong base, and we're going to compare it to the same exact concentration of a weak base like ammonia. And we're going to try to figure out what the pH is for each one. But ammonia reaches equilibrium, so we need a KB. See, we've had KEQ, we had KASP, we had KW, we had KA last week. Now we have KB. Guess what the B stands for? Base. It's just a KEQ. So the KB for ammonia, which we will need, is 1.8 times 10 to the minus 5. Now, if you go back through and study your notes and you look and go, oh, acetic acid's Ka was also 1.8 times 10 to the minus 5. It's a total coincidence. I didn't make those numbers up. Those are actually the Ka and Kb values, but they just coincidentally have the same number. Okay? If it was any other acid or base, it wouldn't be. All right, so we're going to start with strong, just like we did yesterday. We're just going to figure out what the pH is of this. And so I'm going to write the equation. Basically, if you start with sodium hydroxide aqueous, it will, in a one-way arrow here, because this is not equilibrium, completely 100% totally break apart into sodium ions and hydroxide ions. That's what it means to be strong. Please don't get strength confused with pH. Just because it's strong doesn't mean it has a low pH. You could have a strong base and its pH could be 8, just barely basic. You could have a weak base and its pH could be 12, much more basic, because it depends on the concentration of those. Not just all strong and weak tells you is if it falls apart totally or it doesn't fall apart totally. That's all it tells you. Okay. It might be misleading, I don't know. Well, I don't know, because when you rewrite chemistry, you can call it something else. I don't know, somebody just decided to. I didn't write the rules here, I'm just teaching it to you, right? All right, so let's do a strong base. I'm going to go ahead and do a little ice table with this. It's just an end ice table here in order to assess where we're at. Because originally we're starting with 0.0010 molar. And we'll say at the moment it's introduced, there's none of the ions yet. But because it totally breaks down, 100% breaks down, in the end we're left with 0 sodium hydroxide, which lets us know the change. So we lose, we gain. And so in the end we know the concentration of the sodium ion, which is less than helpful, and the concentration of the hydroxide ion. And I know because of my Kw, there is a relationship between hydroxide and hydrogen ion. So a little reminder here, we know that OH minus times H plus is equal to the Kw, which is 1 times 10 to the minus 14. That was one we did last week. So if we know the OH minus, we can find the H plus and take the negative log of it. Or, if I take the negative log of both sides, what I find is that POH, I don't wonder what that is, plus pH is equal to 14. That's another little helpful formula. So here's a helpful formula from last week. Here's a new one. What in the world is POH? I know what pH is. It's the negative log of the hydrogen ion concentration. What is POH? Fado? Yeah, so POH is the negative log of the OH minus ion. And there's a relationship between pH and POH. So I'm going to kind of show you how we can do this then, because what we have in our ice table is we know the concentration of the hydroxide ion, not the concentration of the H plus ion yet. So I explained to you guys, you can find the hydrogen ion concentration by taking this number, plugging it in here, and then solving for the hydrogen ion concentration. And if you do that, then you can take the negative log. Or, we'll do it another way. I'm going to find the pOH. Using this number, the pOH is the negative log of the hydroxide ion concentration, which we can do this one without our calculators. This is 1.0 times 10 to the minus 3, right? What's the negative log of 1.0 times 10 to the minus 3? 3. You can plug it in your calculator if you don't believe me. So the pOH is 3. How many digits past the decimal am I allowed to go? 2, because 2 significant figures, right? So I'm allowed to go 2 digits past the decimal, so 3.00. Then how do I find the pH? Subtract it from 14, right? So the pH is 14 minus 3.00, and so my pH is 11.00, which of course is a basic pH. It's more than 7, which is what we would expect since this is a base. Always be worried. Always look at your pH when you solve for it. If you suddenly get a pH that's under 7 and you're dealing with a base, be concerned. You might have done something wrong, or vice versa. Okay? All right. That was for strong. Now we can whip through weak pretty quickly. Now, this is at equilibrium, so we're going to go through the 4 steps. But here's what you need to know. When you have a weak base and you're trying to write the equation to get your Kb from, take your weak base and react it with water in order to get your products. You don't need to do that with the strong base because the strong bases have OH in them, and you can just break them apart, and that makes it real easy. But when you have a weak base, they don't have OH in them. And so they're going to act as a base Bronsted-Lowry-wise. So here's the example. We're using ammonia, so I'm going to take ammonia, and I'm going to react it with water to write my equation. If ammonia is acting as a Bronsted-Lowry base, it accepts a hydrogen ion. Where is it going to get the hydrogen ion from? The water. What will it turn into if it accepts a hydrogen ion? Ammonium. Because the NH4 plus, the NH3 accepts a hydrogen and becomes NH4 plus. So those two are conjugates of each other. Conjugate acid-base pair. Actually, conjugate base. And this is conjugate acid. What is the other product? OH minus. Because that's what is left after a hydrogen ion gets stripped from it. So this is our equation. And so that's my hint to you, is that anytime you have a weak base and you don't know how to write the equation, always react it with water, have the base gain a hydrogen from the water, and you'll be left with OH minus. So this is your equation. So then I can write my equilibrium expression. So my KEQ is equal to the concentration of NH4 plus times the concentration of OH minus over the concentration of ammonia, but not water because it's a liquid. But you know we don't call this KEQ, right? That's our KB because it's for a base. But again, when we write the KB, it's always the base and water on the left and then the rest of it on the right. It has to always be that way. And then we can do our ice table. You guys know the drill here. We've been doing this a while. I'm not going to fill it out for water because that's a liquid. So I'm starting at 0.0010, and originally I'm starting with none of the ions before anything has happened. How much do I lose and gain? We don't don't know, right? So it's x. So minus x plus x plus x. And then do the math. So the KB is 1.8 times 10 to the minus 5. That's equal to x squared over 0.0010 minus x. You could quadratic it, you could graph it. I will tell you what x equals because you're going to have a chance to practice that on the worksheet in a moment. But you could quadratic it, you could graph it, you could check the 5% rule and see if that would be applicable. I don't really care, but somewhere I calculated it at 1.3 times 10 to the minus 4. So x ends up being equal to 1.3 times 10 to the minus 4 molar when you solve it. But if I go back to my ice table, that is the concentration of OH minus, not the POH or not the pH or the hydrogen ion. So once again, I would do the POH and subtract it from 14. So the POH is the negative log of the 1.3 times 10 to the minus 4. I don't know what that is. 3.89. Here's where people sometimes on a test or something, they're working really quick and they're like, oh, okay, it's 3.89, that's my answer. Because you forgot to subtract it from 14. This is where it's really helpful to go, oh, wait, that's an acidic pH. I was dealing with a base. And so you don't forget to do that other step. So the pH is 14 minus that. So 10.11. And so you can see the strong base is more basic. It has a higher pH at 11 than the weak base. In fact, it's 10 times more basic.